Welcome to Easy Algebra. Today we're going to be looking at functions and function notation. First, we need to ask, what is a function? A function is a relation for which every input has one and only one output. So what this means, for every input x, you have one and only one output y. Think of it like a vending machine. If there's 5 buttons on the vending machine, and you push one of them, and you get a diet soda, and you push that same button again, what should you get? A diet soda. So I have an input of one button, and an output of diet soda. If I push button 5 and I get a regular soda, and then I push it again and I get a lemon lime soda, it's not operating properly. It is no longer a function because I put the same input, button 5, but gotten 2 different outputs, a standard soda and a lemon lime soda. So with a function, you have an output for every input, and you can only have one output when you get the same input repeated. You get to the same output, then repeated. Function notation uses f of x to represent a function. F stands for the name of the function. But you can also have something like g of x. So here we have 2 functions, f of x and g of x. This gives us a way to name the functions. So if we have 10 or 20 different functions that we're working with, we can use different letters to name each one so that we can very precisely reference back to them. Go back and look at function f. Go back and look at function g, and you know which one. Then we have the function rule. So here we said f of x is equal to 2x plus 3. This is a function rule. It tells us whatever input we have here to find our output, we'll plug it in here and simplify this. So let's go ahead and pick some numbers and get some input outputs. We would have f of 2 is equal to 2 times 2 plus 3. And we work that out. 2 times 2 is 4, plus 3 is 7. So f of 2 is 7. So here, we can see a couple of things. We have our input, and we have our output. So one of the nice things about function notation is both the input and the output are displayed in the function notation. So we can put our ordered pair, 2, 7, down without having to reference back to what did we plug in. Because what we plugged in is very clearly indicated right here. So that's why we use function notation. It allows us to keep track of multiple functions using a letter for the name. It also gives us our input and output right there in one place at the end so that ordered pairs are very easy to collect if we're doing multiple inputs with multiple outputs. Now let's look at 2 examples of how this can be used. In our first example, we're given a function. F of x is equal to 2x squared minus 3x plus 4. Find f of negative 2. So here it's telling us our input will be negative 2. Find the output. All we need to do is plug it in. So f of negative 2 is equal to 2 times negative 2 squared minus 3 times negative 2 plus 4. Notice negative 2 replaces x in each location that x was originally placed. I use parentheses here to help clarify a few things. So 1, it shows that the negative is part of what's being squared here. That's important. And then over here, it shows that there's multiplication. This means 3 times x. So this is negative 3 times negative 2. So the parentheses here are important to help us through this process. Now we're going to use order of operations. So we'll start with our exponents. F of negative 2 is equal to 2 times negative times a negative is a positive, so negative 2 squared becomes positive 4. minus 3 times negative 2 plus 4. So now we'll continue with our multiplications. 2 times 4 is 8. Negative times a negative is positive, so negative 3 times negative 2 is positive 6 plus 4. Finally, we can go ahead and add. So here, we could add them in order, and that works perfectly fine, but it's often helpful when adding to remember it's commutative and to look for convenient pairs. So here, 6 plus 4 is 10, 10 plus 8 is 18. So for our final statement, we know that f of negative 2 is 18. That is, the output when the input is negative 2 is 18. We could write this as an ordered pair, negative 2, 18. Let's look at another example that uses function notation differently. We're once again given a function. This time f of x is equal to 3x plus 1. We're given a second function, g of x, which is equal to x squared minus 4. And here we're asked to find f of g, or f composite g of x. The composite is a special operation for functions. When you have functions, it's possible to plug something into one, work it out, and then plug the result into the next function. But we can do all of that in one step using the composite. So here what they want us to do is take g of x and plug it in to f of x. So we're going to take f of x, but where we see x, we're going to leave a large open space. So f of blank equals 3 times blank plus 1. And in that space, we are going to put x squared minus 4, the value of g of x. Now, we can start to simplify it. We can distribute the 3 here. We get 3 times x squared minus 12 plus 1. F of x squared minus 4. We can combine like terms, which in this case is negative 12 plus 1. So we'd get 3x squared minus 11. Finally, we want to go back and rewrite it in the form of the original question, which says that f composite g of x would equal 3x squared minus 11. So what this tells us, if I were to take a value and plug it into g of x and work it out, and then take the result and plug it into f of x and work it out, that would be the same as plugging it into this new function, 3x squared minus 11. So let's test that. If I take 2, g of 2 is equal to 2 squared minus 4, so g of 2 is simply equal to 4 minus 4, or g of 2 is equal to 0. Now we plug that into f. F of 0 would equal 3 times 0 plus 1. Since 3 times 0 is 0, and 0 plus 1 is 1, f of 0 is equal to 1. So finally, let's see what would happen in our composite function. So we plug in the original value, 2, and say f composite g of 2 is equal to 3 times 2 squared minus 11. 2 squared is 4, so we get 3 times 4 minus 11. 3 times 4 is 12. So 12 minus 11 is 1. So we see that plugging it into this gave us the same output as plugging 2 into G and then plugging that output into F. That's what a composite function does.